race, yeah.
Homework, the first problem, can I ask?
Written homework?
What?
Written homework?
Yeah.
Okay, what's the first problem?
It's evaluate two intervals. Should we use like spherical coordinates, or can we like break it up and use?
Spherical isn't so much fun, is it?
So can we break it up and use the root pi over 2? We already.
Yeah.
See, remember when we did the integral of e to the minus x squared,
Can we use that?
we switched to polar, and then we had, by symmetry, you had an e to the minus r squared times r from the fudge factor, and that made it perfect.
Yeah.
But now if you're in more dimensions, your fudge factor is going to be rho squared when you have e to the minus rho squared, and that, you can do an integration by parts, but you...
It was just...
Use the polarity.
I was thinking.
So you are allowed to use what we've done in class and what's done in the book. You do not. So figure out the easiest way to do the problem. Next. Be warned, if you guys are planning on coming to office hours today, I expect it to be a zoo from the other class. I may be wrong, of course. Llama.
There's going to be a lot of people lying around.
We've got that on tape.
Got it. You're showing your true stripes.
I kind of think at the end of this lesson, we should actually have a group of real people acting
Crazy.
Bloopers clips. Any serious math questions?
selected clips from Shifrin's class.
Not counting puns.
So we're not allowed to say puns anymore?
No, you're allowed, within reason. All right, so last time we were sort of rushed at the end of class, but I got down to the formula with the guys rolling down the inclined plane. We got the masses actually canceled from the formula we had, and we had the following formula: 1/2, 1 plus this weird ratio of the moment of inertia to ma squared times magnitude of velocity squared. And so the masses disappeared except from this ratio.
What ratio?
Brutus is going to come after you, be careful. All right, and so I made the argument that this formula holds at any point in the trip when they're rolling down the hill. So given that you've gone down a height h to this point, this formula holds at that height that you've gone down. And therefore, the velocity of the one that wins needs to be biggest all along the way at every step of the travel. And so to make velocity biggest, you want this coefficient smallest, since this side is independent of the geometry. It just depends on how high you've dropped. So fastest, if and only if I over ma squared smallest, and indeed you get the ordering on who comes in which place in the race according to the size of this, going from smallest to largest. Agreed? So let's actually make our table here, and let's try to fill in some of the data points here. So we had a hula hoop, or a hollow cylinder. So basically a hula hoop, for all practical purposes, is a ring of mass at distance a from the center. If you take a cylinder of radius a, hollow cylinder, it likewise is a ring of mass at distance a from the center. Right? Hollow cylinder. Then every particle is at distance a. And so what's the moment of inertia going to be? It's going to be exactly ma squared, because remember that to do the moment of inertia, we're either adding masses times distances squared from the axis, or integrating density distance squared over the region. So if all the particles are at distance a, the moment of inertia is ma squared. Mm-hmm.
Oh, okay, so a is a distance, not acceleration.
Yes, A was the radius that we were rolling on. So all these particles have some radius A. All these objects have some radius A. And they're rolling about an axis, therefore, whose distance from the edge is A. So here we're going to get I over ma squared is exactly 1.
Why is one?
Because we just said that for a hollow cylinder or for a hula hoop, which you can think of as a very thin circle, I mean, if you prefer, you can make it a little cylinder here, right, that has some thickness, and then it's exactly this question. Right? So all the particles are at distance A from the center, if you have a circle. Same thing here. If you have a hollow cylinder, all the mass is at this distance A from the axis down the middle. So you're going to get ma squared for the moment of inertia, which means the ratio is 1. And that's the biggest it can be. So the hula hoop, in fact, comes in last. Or a hollow cylinder. What else did we have on our list? We had a solid cylinder. So I'm not going to say it's a can of soup because I got criticized last time. You could have a solid ball. You could have a hollow ball. And somebody last time mentioned, it might have been Lama, I've forgotten, a double cone.
Yeah, it was. It was not me.
It was not you. Who?
Patrick.
It was Patrick? Okay. I forgot. Sorry. So do a solid double cone. So that thing, you can imagine putting wheels here. Well, you don't need wheels, you just let it roll. Right? But this thing has radius A. So the solid cylinder, we actually did this calculation. Last Wednesday I did the moment of inertia calculation without having told you that it was moment of inertia. Do you remember what the answer was? No, solid cylinder.
Solid cylinder last Wednesday.
It's the last example I did with cylindrical coordinates. I integrated distance squared from the
The
axis.
volume of the cylinder times its radius squared over 2.
Half a square.
So the volume would become the mass if you put a density in there. And then you have 1/2 of ma squared. So the ratio is 1/2. Solid ball, I don't think we've done. You guys are doing the hollow ball in homework. Dennis, what was the answer? 2/5?
2/3.
2/3 was supposed to be the answer.
2/5 was what I got. It was no.
Right, 2/3 is what you're supposed to get. So this is homework. It's in the book.
Gives you the answer though. Why?
Now the solid ball is not.
Okay, so
I'm going to do the solid ball now. So I want to do the moment of inertia of a solid ball. Of course, we're again doing constant density. If you wanted to do variable density, that's going to change the moment of inertia, right? Because if your mass is more highly concentrated out on the edge than it is near the center, that's going to make these terms bigger when you're further away, and so that's going to make the moment of inertia get bigger. If it were very heavy at the center and very light out here, that would make the moment of inertia smaller. But I'm going to assume uniform objects here. So we want to do the solid ball. We want to find the integral of, again, distance squared from the axis. And so in spherical coordinates, we're going to want to integrate distance squared from the axis. That's going to be what in terms of spherical? Rho. Guessing is not good. Rho sine. Here is your right triangle. There's phi.
Rho sine theta.
rho sine phi squared, fudge factor.
Phi squared sine phi.
Rho
Sorry,
sine.
sorry. It's a P.
Yeah.
d rho, d phi, d theta. Theta goes from 0 to 2 pi because you put the center at the origin, of course. Phi goes from 0 to pi, rho goes from 0 to a. So, we're going to get 2 pi from the theta integral without any further ado. We're going to have the integral of rho to what power? Fourth. Integral of rho to the fourth d rho. So you're going to get a to the fifth minus 0 to the fifth over 5 from the rho integral. Bless you. And then I have one which you guys can't do in your head so easily. Unless you've already been doing your homework and you've done it several times. Yes? No?
Wait, okay, then is that?
You need to sub for sine squared just to 1 minus.
Cosine.
Oh, just memorize it's 1/3.
Blah, blah, blah. So let's see.
1 minus cosine squared times sine. And then you can do it by an easy substitution. So the integral of sine is negative cosine. That's going to give you a 2. Integral of cosine squared times sine is going to give you negative 1/3 cosine cubed. Evaluated at 0 and pi, and so I get 4/3 here, which means I get 8/15 pi a to the fifth. Looks familiar, hey, Dennis? All right, so I still want to figure out what that looks like relative to mass times a squared. So if I factor out an a squared and a mass, what am I left with? Well, what is the mass? I left out the density, right? I mean, there's a density that's really multiplying everything.
4 over 3 times
But
a cubic times delta equals to the.
right, so the volume times delta is the mass, and the moment of inertia should have had a delta. Those are going to cancel when I do this, right? You get a factor of delta there, a factor of delta here because of the fact that delta is constant. So let's assume delta is 1, because it's going to cancel out anyway. What's the volume of a ball of radius A?
4/3 pi
A cubed.
All right, so what's left? Looks like a 2/5. Does this surprise you, by the way, that this number is lower for a solid ball than for a hollow ball? Why not?
Because it's
The
solid
closer
ball
mass
has
is-
closer mass in the middle.
There's more mass towards the middle on a solid ball than there is on a hollow one where it's all further out near the edge. Well, it's all on the edge, but the distance from the axis varies still. All right, double cone.
Can we do one cone and double it?
I don't know, what do you think?
Yeah, I think so.
No.
If you treat
Well,
the
because
center,
we're-
treat the center mass
cone
at
wouldn't
the
roll.
point.
Well, it's not going to roll if it's not a double cone. But to do the moment of inertia calculation, if you're doing this region,
You just
is not the integral. Well, my picture's slightly asymmetric, but if it were symmetric, like it was supposed to be,
Is this a solid cone?
you make
or-
us
It
get
is a
that about
solid cone.
pictures when you complain about your
Is it generally that solids do better than
Yeah.
non-solids?
it seems that way, doesn't it? Do we agree that whatever integral here doubles when you do both of them?
if you could if you keep the center mass at that part in the middle.
Huh? I'm still doing the
Yeah.
moment of inertia about the z-axis.
Alright, yeah.
Sines for cylindrical.
2 times.
So, well, so do we want to do cylindrical for this for a change?
Yes. Yeah, because the top.
So we'll do the top half, and then we don't have to double because we'll just take the volume of the top half, and both of them would have 2, right? So you want to use cylindrical. And I'm going to again assume delta is 1. So what do I integrate? If I want square root of the distance from the z-axis?
R squared.
R squared. Fudge factor?
R,
dz, dr, d theta. Theta goes.
0 to pi.
Now we got to stop and think. If we're doing cylindrical, we have to take the region and do what with it? Project on the xy plane. Good. When I project this guy, what do I get?
Circle.
A ball or disk of radius A. And for each fixed point,
Z goes from 0 to.
No.
No, from
No,
the
from
cone.
0.
Oh, there, no, from 0.
It goes.
What is the height?
You have the top. Top is the side.
Yeah, what's the height? Is that
Height's just
now we're not
H.
doing spherical, we're doing, you guys maybe do cylindrical.
Height's just H, so it goes to H.
Yeah, but
So the cone we're going to have has some height h,
okay.
and we haven't specified the shape of the cone, right? We don't know the slope.
We'll figure
Well,
out.
now we do in terms of h, right?
I guess.
Right, if you've got the line here that rotates around to make the cone, you know that this height is h when this radius is a. So in general, if you use what?
Similar triangle.
No.
Ratios.
What's this called? What kind of triangles? Similar triangles.
H over
So
times R.
z is to r
H over H times R.
as h is to a. So z is given by
H R over A.
agreed? So that's where it enters. It enters on the cone. And it exits when z is h. Everyone agree? Well, I can't quite fit it on the board, unfortunately. Raise and lower and raise. All right? So 2 pi, integral from 0 to a. What's the integral dz?
Z.
From blah to blah. And the r cubed is constant. So we have r cubed times h
And 1 minus.
minus h times r over a. And then we're integrating that dr. So the h pulls out. And I have the integral
R cubed.
r cubed
fourth.
minus r to the fourth over a. So what do we have?
R to A to the fourth over 4.
A to the fourth over 4 minus
A to the fourth over 5.
a to the fourth over 5. Everybody agree? A fourth minus a fifth, be
120.
1/20th. So this is pi h over 10 times a to the fourth.
And the area of the cone is.
Volume
3-dimensional area of the cone is
1/3.
1/3.
pi
R
r squared is a squared h. Remember we're doing upper cone only, volume of upper cone only. So if I do I over ma squared, what am I going to get?
10 over 3 times A squared.
Whoa, no.
No?
So there is an h, if you divide, let me write this out. Pi a to the fourth h times 1/10 over pi a squared h times 1/3. So what do I get? You had it upside down.
Yeah,
3/10, right? Ooh, the race is getting tight here.
We say that whichever object wins this race is definitively the fastest shape, or is there a fastest shape?
I asked that question on Friday.
And three, is that gonna be 3
So-
times a squared or just 3/10?
Remember, we've divided by.
That's just the
Oop, 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 oop. Sorry, thank you. All right, where are we?
So it didn't,
So far, who's winning?
Double cone.
The double cone's winning,
so it didn't
but
depend
the
on-
solid ball's not far behind,
My design.
does it? Doesn't depend on the shape of the cone. You take a very fat cone or a very skinny cone, they're going to get there at the same time.
So what happens if we take like a hyperbolic type of thing?
So it,
So yeah, so Cameron's asking what happens if you take a shape that's more like that, rather than being linear.
Probably be better.
yeah, what if we just like compress it into?
No, is it better?
No, it's worse. Because it's far, like, when you close to the center, it gets skinnier.
So would you want to do like the opposite?
That feels better.
Yeah, like bowed out.
So what if you bow it the, what if you make it
Yeah.
like that?
No,
Now
that's
that looks worse.
Yeah. So
That's
should
better.
be maybe like a wheel and axis, like just 2 wheels and an axis.
Aha.
Well, you want all the mass on your
Like
axis,
that's
other
what
than
the
you have
arms,
no.
you know.
So,
Yeah, two discs.
so Ken's on the right track.
I like that.
The thing that ought to win should be something all of whose mass.
It's on the axis of rotation.
All
Yeah,
the
but
mass
but
goes-
the rotating. So if the wheels are going like this, the axis of rotation is here. So if you made a rod that was very thin
massive.
and made the wheels massless, then the mode of inertia would be 0, effectively.
Couldn't you just,
So then
why
why
would
not?
you need wheels if you had a rod? You just roll
Yeah.
a rod. It'd be like
No,
a really
I don't
narrow
know.
No, but then if you're having an actual rod,
Yeah.
then it's a solid cylinder, and now you're not winning.
What happens if you just make the mass?
What
less
if it's
big?
like?
This didn't depend on A, did it? It's very subtle, Patrick, actually. So,
Why do you always deal in subtle things? Can't we just deal in like blatantly?
Blatantly obvious.
speaking like a true statistician.
So what are the wheels doing that?
They're like massless, right? Because the wheels are so narrow.
makes it different than
Oh, yeah,
a
that
solid
is
cylinder.
interesting, yeah.
Aren't you assuming the wheels have like no width, pretty much?
No, I was putting actual wheels there, but saying their mass was infinitesimal compared to the mass of the rod. So I have the A is still there, but there's no mass out here,
That really
basically.
helps because then the rod wouldn't be spinning as fast. I mean, it'd be having the
Is the
same.
rod spinning at all? In fact, if you do this,
It depends if the
Well,
rod's
I thought
connected
it
to
was
the
a
wheel.
rigid body.
Yeah.
well, what if there's a bearing here and the rod just gets to sit there and the wheel rolls?
Is it very much
Then
Yeah.
now Patrick sees the difference because you have no rotational energy coming from the rod.
But if the rod were rotating, would it be 1/2? If the rod were like,
No, it
if it
should
was
stay
rigid,
zero.
would it be
It's
1/2?
not rolling on that
Yeah,
radius.
I feel like if we make the wheels.
So if the wheels are big, even if this isn't infinitesimally thin, the moment of inertia from this part divided by a big A squared, this part's going to go to 0.
Wouldn't you have a different density though?
You would. You'd have to think of this as being made out of 3 pieces, the wheel, well, 2 pieces, the wheels and the rod, and you do the separate computation, adding the 2 moments of inertia. Okay.
What if you had uniform, one of the uniform density,
If you require
and no bearings, no nothing, you just had essentially what looked like
a rigid body.
Well,
rigid
but
body.
do you let me make the radius of this tiny?
Yeah.
So you just get huge wheels. and
So big wheel makes A big, and tiny radius for this makes the mode of inertia very small because the stuff's all very close to the axis of rotation.
Yeah, and so
So it's still going to get close to 0, won't be at 0.
And so because there's, I guess, uniform density, you'd have to make it the
The wheel's very narrow.
you'd have to make the wheels more narrow and the rod a lot thinner to make everything to compensate by making it closer. If that makes any sense at all.
Longer and longer.
Yeah, you can make the rod really long.
Yeah,
Yeah.
make the
Okay,
rod
or that.
Does that Oh, you mean all the, how does the length of the rod matter?
Because then you can
Because
compensate
then
for
it's
it.
all
It adds more mass in there.
Compared to the other object.
It would add more mass closer to.
Oh, more
We're
mass
saying for a
close,
given
I see what
object,
you're trying to do.
yeah. We're
Okay.
saying for a given
Also,
object.
What if you
Given
do it with
mass.
just one wheel and you can make sure it balanced? So you put the wheel.
Oh, you're unicycle.
If you just,
Then you lose mass from the
I mean,
wheels.
we're making the wheels.
I was making the wheels
yeah,
out of
arbitrarily thin, so.
whatever they make spaceships out of, very light metal compared to the
so
rod.
why don't we just put tiny wheels in the bottom?
So this can get as small as.
If you-
All right,
You get like a motor.
I'm gonna let you guys have fun with this on your own time
You're
at this
16.
point. I'm done.
We already
So-
spent our time on your stuff.
So I want to make one more physics remark, although I'm not giving you homework on this unless you
The
choose.
wheel and axis is a reason we use it.
Hmm?
So I guess mathematically there's a reason we use wheels and axis. As opposed to just double cone.
Well, double cones aren't too practical.
That's it.
Do you think when you were designing, like, the way it's when in different how should we design wheels, did they go through this mathematics?
No, they probably just tested it.
Yeah, probably just.
I mean, how many times do we take trips by rolling down inclined planes with only gravity accelerating us?
I used to have
There's
another
some
time.
other.
There's education.
All right, so another application of this stuff goes back, in fact, to Newton, who was actually, among other things, trying to understand what the gravitational field outside the Earth was and inside the Earth, assuming the Earth was a uniform round ball. So we'll actually have a slick way of doing this in Chapter 8, but I do want to mention that if you wanted to compute the gravitational force, that again fits this same setup where you have, say, a test mass and some blob, and you want to know how much force is the gravitational field of the blob exerting on the mass m. And if you're actually interested in seeing how Newton did this stuff, it turns into an interesting single integral problem for doing the case of the uniform ball, and that is at the end of the section.
What's that M word?
Gravitation,
Oh, that's G.
that's an R, and that's a VI,
Okay.
And
I
that's-
started with an M.
that's a G. So again, you're going to do the same idea that we've been talking about for the last few days. You're going to imagine chopping the blob into lots of little chunks, and then say each chunk exerts a little bit of force, and you're going to add up those little bits of force and say, what's the net force of the assemblage of chunks? So what if you took a little bit of mass here, so Newton's law of gravitation, which we will again come back to later on in the course, says that if you have a mass capital M, it's going to attract a mass little m proportional to the product of the masses and inversely proportional to the square of the distance between the two. And then there's a vector here, which I'll write as a u at the moment. That's a unit vector between little m and big M.
We actually talked about this last semester, right? And you said we would learn why there was it was 2 exactly.
Yeah, why did we talk about it?
I don't remember. We were talking about central
No,
force.
this was one of your.
Oh, when we were doing, right, we were doing
Previews
planets,
for this
right,
course, and you
Kepler.
said- you
That's
said we
right.
would find out.
We're not there yet.
All right.
We're not there yet. So u here is the unit vector from the little mass to the big mass that's pulling on the little mass. Of course, big M might be smaller than little m, but. Okay, so it's pointing it away from little m. In particular, if we put little m, the test mass, at the origin, then we could write this, and I think I did have this now that you've reminded me last semester. F would be G, M, little m, and then position vector of wherever the big mass is over magnitude cubed. Why cubed?
D squared, x cubed.
Because you make it into a unit vector and then you divide by its magnitude.
Right, so it's magnitude of x squared, and then the unit vector is x over magnitude of x. So this is the way you write down an inverse square force, even though it has a 3 in it. So if I wanted to take a mass distribution here rather than a single mass at point x, I would want to approximate my blob as a bunch of point masses put together, and I would take that the net force would be the sum over however many masses there are, G, little m, big M, x sub I over magnitude x sub I cubed, sum that over the masses. And if you imagine then the case of a continuous mass distribution, you're chopping into smaller and smaller chunks, and then this becomes GM integral over whatever region I have here, whatever my blob is. The mass of the little chunk becomes density times the volume of the little chunk, just like we've been doing, and then you have x over magnitude x cubed. So you're integrating a vector function just like we talked about for center of mass. But instead of doing the center of mass calculation where you do the weighted average of x, now you're doing the weighted average of x divided by magnitude x cubed. And so you could do some problems where you actually try to do some of these integrals. And if you're interested, there are a couple of really interesting problems that I'm not making you do in the book, and you can take a look at some of them and see if any of them strike your interest. Okay.
Would that work when little m is similar in size to big M?
Mm-hmm. Mm-hmm. Yeah, I'm just saying, think of the force the big mass, as it were, exerts on the test mass. And then the reverse, the little mass in this picture, whatever it is, pulls the big chunk exactly the same way backwards, equal and opposite.
I guess I'm just wondering if you're treating little mass like a point, why can't you treat big mass like a point?
Because
so
you can't do that.
So I gave you an example. Yeah, that's a great question. I warned you about this last Friday. So let me re-warn you. Suppose the test mass is sitting here, minding his own business, and up come two giant masses and put themselves one very close to the test mass and one very far from it. Then Jackson, you would agree that the center of mass would be here. The center of mass of the two blue guys.
Right.
And so the center of mass, if you put a mass 2m there, would then exert a force pulling in that direction on little m. Agreed?
Yes.
But in truth, what happens? It's actually, because it's so close to this mass is basically inconsequential, and the actual force is quite strong in that direction. So you cannot compute the net force of the blob by putting the center of mass of the blob.
So as little m gets close to the blob, that sort of example might be important.
Well, so this is why Newton's discovery is so cool. And again, we will prove this in chapter 8. Newton did prove that if the blob is a uniform ball, then you can concentrate it at the center of mass, provided little m is outside. And what Newton wanted to understand is what happens if little m becomes inside the blob. And that's what, how many of you know that? I assume you did it in physics, and Jonathan knows it. So we're going to actually prove that in a few months.
So pointing to the center of the ball.
At the center, if the mass is at the center of the Earth, there's no force.
Oh, but if you're like in the ball,
Yeah.
I guess.
The question is, what is the function?
Then it's no longer going to be an inverse square force. It's actually going to be, we'll prove, linear in the distance from the center of the ball. So we'll prove soon, toward the end of chapter 8. And this is also at the end of the section that we're in now, Newton's result, is it? Or see page, whatever page it is. .305, 306. That the force due to the uniform ball looks like this. So if your radius of the ball is r, outside radius r, it looks inverse square in the distance from the center of the ball. So if you're on the surface of the Earth, it is g, mass of the Earth, mass of your test mass over radius squared. And then it continues to be inverse square. But what Newton figured out, and somewhat surprising, perhaps, maybe not, is that it's linear on the inside. It's like that. So if your distance from the center of the Earth is less than the radius, then the gravitational force is proportional to your distance from the center. Okay, so we will do this as part of our discussion of why this is a 2 later on.
Did he just figure this out, or did he run tests and kind of?
Now this is one of the reasons he invented calculus. He wanted to understand this. And if you look on these pages, that is the calculation. I'm pretty confident. I looked this up at one point when I was younger. That's pretty much how Newton did it. It's a single integral question. You don't need multiple integrals. Okay. Any other questions on this? All right. So for the people in the crowd who are tired of physics, we now have a change of gears. Now we're back to linear algebra for a bit.
Oh, no, I'm in clutch.
Double clutch.
Back to the future.
So you guys some of you have been curious of where those fudge factors were coming from. Some of you. You will recall from chapter 1 that if you had two vectors in the plane, that the determinant of the matrix that had them as columns gave what?
The area.
The signed area. Since doing integrals is about chopping things into pieces and wanting to know areas and volumes of pieces. And then we had the parallelepiped in 3 dimensions. And so I promised you a discussion of what happens in n dimensions. And it's not going to be surprising that determinants tie into integrals because exactly determinants are used to figure out volumes or sign volumes. So we're going to see now that in n dimensions, determinant, which we have yet to define, will give sign volume of n-dimensional parallelepipeds. So what I'm going to do basically is state a theorem that we will mostly prove in the next few days, that determinants are uniquely determined by having a list of properties. And those properties are going to be very similar to the properties we had in chapter 1. So the theorem is going to be, there is a unique function, which I'll call script D, which takes n vectors in Rn in order. So how do I take n vectors? Well, I take Rn cross itself n times so you're going to pick a vector in Rn, pick another vector, keep going until you've picked n vectors. You're going to have a real number output. And I have to say there's a unique such function with the following properties. So you've probably forgotten this from chapter 1. Anybody remember it? What properties we had?
If you switch any to
Oh, yeah.
vector inputs, it negates, I think.
So you get a minus sign if you switch two vectors. So if you take v1 to vn, and I'll make it clearer by putting an I in there and a j in there. And now I'm going to switch the I and the j, then I'm going to get a minus sign. So I'm not switching anybody else. I'm putting j where I was and I where j was. So here I and j are different, of course. Okay, so if you switch to, so remember when we said if you switched v and w, you change the sign on the area, on the signed area. Okay, that's one.
Pull out
You can pull out constants.
I'll pull out a constant from any particular slot. So if I take v1 and put a c in the ith entry, the c pulls out, and that's true no matter which I you pick and whatever scalar you pick.
There's another one where if you added two columns, you can split it into a
Okay.
sum of two different derivatives, or
Good.
determinants.
And in fact, those two put together sound a lot like what? Linear maps. So linear in each variable separately. And there's a word for that. It's called multilinear. So d of v1, and now I put the sum, as we said, of two vectors in the ith slot, then it becomes the sum of two determinants, one for each. Okay. So these two rules put together, as I said, get the name multilinear. Okay, what else?
That if you have v1 and two v1s in the same, or like two of the same vectors, then isn't it 0?
Yeah, but I don't have to list that because that already follows from what we have. Which one does that follow from?
From 1.
From 1. And there's another variant, which I'm going to derive in a minute. So it's multilinear. This is called alternating. Because when you switch, you get a minus sign. That's just mathematicians call that an alternating tensor. And then you need one more property.
The zero vector?
Nah. So far, there's nothing to say that I couldn't just take whatever function you had in mind and multiply it by pi and have another function. Or by 17,422.
What? sorry, what are you saying?
There's nothing here. Suppose you had a function that satisfied these. I could take your function and multiply it by any constant,
No.
and it would still satisfy the rules. So if we really want to be measuring volume, we better normalize, there's that word again, by saying that, put in the standard basis, you should get the volume of the unit cube, and it should be 1. So here the E1 to En is the standard basis. And that actually is a theorem. So there is a function that generalizes what we had in 2 and 3 dimensions, and it actually is uniquely determined by these properties. Now what we're going to do today, basically, is just use the properties to actually compute with it, and then we'll learn more tomorrow and Wednesday about it. And come up with different ways of approaching it. So Gabe did comment that if 2 of the vectors were the same, you get 0. Oh yeah, before I go on, let me just say that we set determinant of a matrix to be D of what? What do I do with a matrix so that it fits this? Use the columns. So remember, little a's are the column vectors. Okay.
It has to have the n by n.
It has to be square. Yep. When they build the next classroom building, I hope they design it better. All right, so Gabe observed that if Vi equals
You want me to zoom
Vj,
in, Gabe?
that 1 tells us that if you switch, if these are the same vector and you switch them, you've got the same quantity, but it's supposed to change to negative itself. So if you have repeated vectors anywhere, you get 0. That's like saying that the area of a parallelogram when you use the same side twice is 0. Not so fascinating. But you might recall that we wanted to be able to do stuff where you combine these rules and somehow talk about the analogs of row operations. But now we want to do column operations for the matrix. What about D if you take the ith vector and add some multiple of it to the jth vector?
It doesn't change.
Again, I not equal to j.
Well, then you split that up into 2,
Split it up.
Use
Sum
use 3, split it out, and 1
determinants, and then
0.
pull the C out of
Yeah.
one.
In the first
so it makes
So
the.
if they don't go 0.
So 3 plus 1 is not 4.
0.
It tells you that adding this term, oh, we have to use 2 also. So you guys are telling me split it into 2 using property 3. And then one of those terms will have a VI and a CVI. So by what Gabe observed plus property 2, the C pulls out, and then you're left with 2 VIs in 2 places. You get 0. So it didn't change it. If you add a multiple of one vector to another, whoops, I said I did it wrong. You add a multiple of VI to VJ, it doesn't change the original.
So you can pull out multiples and such.
No, you can't pull out multiples because those pull out C's. But if you have a multiple of one vector added to another, what's the geometry of this?
So you want a linearly independent set of vectors.
Well, we're going to get to that tomorrow. But when you add a multiple of one vector to another, what's going on geometrically?
You mean
Suppose-
head to tail thing?
No, if I had VI here and VJ here, and I added a multiple of VI to VJ, remember I'm doing what?
Oh, so
You're going to the corner.
sliding it. That's
What's the word? Shear. Shearing the parallelogram doesn't change the area in this case, or the volume in general. That's what this property is saying. Okay, so what we're going to do tomorrow is start off by actually doing a numerical example, and then we're going to start figuring out properties of determinants that we can get from these so that we actually get some nice structure in terms of general matrices.